Welcome to Module 4 of Foundations of Machine Learning. At the end of this module, you should be able to formulate supervised regression and its pipeline. You'll be able to write down and interpret squared loss, empirical risk, and the normal equation solution for multivariate regression. You'll be able to implement linear and polynomial regression in Python using NumPy and scikit-learn, and you'll be able to compare closed form versus gradient descent. You'll be able to visualize cost surfaces in weight space and interpret gradient descent trajectories. You'll be able to explain and demonstrate why naive regression is a bad classifier and how this motivates logistic regression. And you'll be able to derive or follow the gradient of the logistic loss for a single example. Furthermore, you'll be able to apply basic rules of thumb for train, validation, and test splits and diagnose simple forms of data leakage. So it's going to be a big one. The supervised learning pipeline essentially consists of these components, normally all the way through, sometimes a subset. But it's a sequence, it's a series. So normally we need a problem from stakeholders. What is the decision? For whom is the decision being made? What kinds of real-world costs exist for making errors? Then second, what data or labels do we have? How are X and Y measured in the first case? Like who's providing the labels? What is the actual data generating process? Third, we will split the data into training, validation, and testing, or at least training and testing, and we won't be doing any peaking. Fourth, we'll choose a model family. Are we going to do a linear model, a tree, a neural network? These come with their own questions about capacity, interpretability, and other constraints. Fifth, we will choose our loss and our metrics. What loss do we use for training? What metrics do we use for testing and evaluation? And how do those relate to the decisions we're going to have to make? Then we'll actually do the training. We'll minimize the empirical loss on training data. Maybe we'll do that with regularization, which we'll talk about later. And then once we've completed that task, we will evaluate and stress test. We will do this on validation or test data. We will look for any kind of leakage or any kind of bias or any kind of distribution shift. In other words, we will think like an engineer or ship like an engineer, and we will look towards deployment and safety. And finally, we'll actually do the decisioning and the deployment. Choose thresholds, add guardrails, and add monitoring. So we talked about this in Module 2. Supervised data set consists of pairs. This can be described in many ways. We had a slightly different notation last time, but it's basically X, like the ith data point consists of input variables X and output variables Y for n data points. We can put all of these inputs into a big matrix, big X, which usually will be a matrix of real values, and its dimensions will be n rows of data points and d dimensions or columns of variables or features, which so far we can all describe as they're all synonymous. Our targets will be a vector, at least for now. This is Y. This is a real valued vector of size n, because we have n data points. We have n labels, one for every data point. Our model family will be some parametric function. The parameters are theta that maps our big data set R of d dimensions to R. So for a d-dimensional data point, like a row in our big matrix X, predict a single real valued number for a regression. So a linear regression, it takes this form down here. So that's X multiplied by some weight matrix or slope. This is normally going to be just a single number if we're doing it as simply as possible. And B is the intercept or some kind of offset from the origin. So again, f sub theta of X is our model. And this is the form it takes for linear regression. Y hat will be our prediction from this model, which might be different than the actual label. And in this case, the only things we can really fiddle with, because we're given X and Y, we can fiddle with weight W and bias B. We'll talk about these soon enough. Our loss function, again, loss function just compares a prediction on a data point against the actual label for that data point. This will measure how bad it is for us to predict Y hat, given that the truth is Y. And often, and in our case, this is going to be the squared difference. So what is the actual difference between these numbers? The difference can be positive, the difference can be negative, depending on whether or not I've overshot or undershot the truth. So just to take care of that negative positive dichotomy, I will square it. This has other benefits to it as well. So our metrics, this is basically a summary used for evaluation and deciding whether or not this model is good enough. Mean squared error, mean absolute error, accuracy, and recall, which we'll have to get to, are all reasonable metrics. And then training. How do we actually modify or choose our parameters theta to make the average loss, to make the empirical risk, same thing, as small as possible on the training data? So again, the game is kind of, we're playing with the world. The world has this probability distribution that we don't know about, that is kind of a function of x and y, inputs and outputs x and y. And it's producing data according to this probability function, and we sample a small subset of what could be sampled, and that is our data set. We want to choose a model that maps from x onto y prime, y hat rather, and for every sample we pay some kind of loss. So again, if we care about the average loss on new unseen data, this is again our familiar expected risk. So our expected risk hypothetically is like some known expectation of what is the loss over all of the possible x's and all of the possible y's that can be drawn from some probability distribution p. But again, we haven't seen p directly. We only have some small sample of data. We only have a finite sized data set. So we have to approximate this expected risk using the empirical risk. So we've saw this already. So the empirical risk is, again, looking at every loss between a prediction on a data point and its real label. We can sum over all of the losses and take the average. This is our empirical risk. Sometimes this is called the training objective. Sometimes this is called the cost function. We'll use these terms in slightly different ways in different scenarios, but for the time being, these can all be considered to be synonymous. Given this function, we can then try to find some value of f that will minimize this function, right? So minimizing the empirical risk. This f is our function, but really what we're doing here is finding a set of parameters that parameterize our function f, right? So we can change the shape of the function f in such a way that we minimize our loss. Whatever function is what we have obtained that finds us the minimum loss, that is our preferred function. That is the best function according to our empirical risk. We call that f hat. So like through the training process, we'll find this argument, the argument that minimizes the loss, and that's our function that we choose. That's the function that we like. So here, script f is this our model class. So this can be like the set of all possible linear functions. And we want to try to find like the exact linear function that minimizes the loss, or minimizes the empirical risk, minimizes the loss on average. So suppose we have 3 labels, 10, 12, and 9, and our model is always predicting 11. So y hat is our prediction, and it's always 11. So the squared loss here, we have a couple of them. So 11 minus 10 is 1. 11 minus 12 squared is also 1. And 11 minus 9 is 2. Square that, it's 4. So those are the squared loss for each of our 3 data points. The empirical risk is going to be the average of these. So the loss on the first is 1, second is 1, third is 4th. So it's just 1 plus 1 plus 4 divided by 3. The average is 2. So our empirical risk, our mean squared error, because we're finding the average of our squared errors, is 2. So this is our training loss, or our empirical risk that we print. So if the loss function, given a function that's parameterized is small, then on average, that function makes small mistakes on new data from the same data generating process. The same distribution that's generating data will generate data that's similar to what we saw before. So therefore, if we minimize the expected loss, we should expect to do well in the future too. At least that's the idea. We're never going to see P directly. Like P is always going to be something, P is the probability distribution, however it's shaped, that we'll never actually see. We always have to approximate it. So the expected loss, expected empirical risk shown here is theoretical. Since we don't have P, we can't actually measure this exactly, but we can estimate it empirically, i.e. through experimentation by just using the N data points that we do have. So again, in regression, squared error is what we call L2. We saw this a moment ago. This is just the difference between our prediction and our actual outputs squared. This will penalize big errors quadratically. So the bigger the error is, those errors are going to be squared. So errors are going to increase the worse your expectations are. So the worse your model is doing, it's going to be penalized more and more. Using this error, if we're just averaging these squared errors on every data point, this gives us a mean squared error. Absolute error, or L1, is different. So it's still the difference between our predictions and our actual labels, y hat and y respectively. But now instead of just squaring it to get rid of the negatives, which we don't care about right now, we just take the absolute value. Right? Remember, these bars are for absolute value. I know you all know this already, but I'll occasionally just touch base on some of these basics. So here, a big error will be penalized linearly. Like if an error is 10, for example, the loss on squared error will be 100, and the loss on absolute error will just be 10, right? So you can see what the difference is empirically. If I'm measuring absolute error between predictions and actual labels, then taking the mean, as you might expect, is the mean absolute error, or MAE. So when I say MAE, that's mean absolute error, and MSE is mean squared error, and you can see why. So here's a little tiny example. We have a true value, y is 50. We have models A and B. Model A predicts 55, model B predicts 65. We take the actual differences between these. So model A is only 5 away. 5 squared is 25. B is 15 points away. So that difference is 15. Squared is 225. So model B, with that difference in absolute terms of 10, is 9 times worse off. Right? So it's 10 times more points. The absolute error here is 55 minus 50 is 5. 65, the prediction, minus 50, the truth, absolutely is 15. So the absolute error we ascribe to model B is just 3 times worse than the one we ascribe to model A. This is like direct, it's like the actual error, but it doesn't penalize as much. So here's a fairly easy question. This is one of the situations where I could have put the little pencil emoji. Think about it for a moment, write it down in your notebook. Which of mean squared error or mean absolute error reacts more strongly to outliers? So if you have a lot of data in a particular point and they're all very close to each other, generally, but there's outliers which are very far away from everyone else, models are going to make errors on trying to predict them because they're so atypical. And here I go again. I'm going to zoom out so you don't have to see me up close. This is for your benefit. Which of MSE or MAE will overreact to some extent to these outliers. So let's start with one-dimensional linear regression just to get the ship moving. This is the simplest regression problem, so it's important that we can understand some of these key concepts because they'll keep on coming up over and over in more complex models. Our input right now is just a scalar, a single number x, which is a real valued number. Our target is going to be some other real valued number. This could be an exam score. You get anywhere from 0 to 100 or any fraction in between. And our model, in this case, will be a straight line. Here, we'll call the straight line w sub 1 times x plus w sub 0. So again, our parameters are w sub 1, w sub 0. Often when we have parameter sets, these are basically sets, but they're ordered. So we use these angle brackets usually to describe sets of parameters. Here we have 2 that we can fiddle with. So our parameters theta can be described in various ways. So a few moments ago, we had W and B serving these exact same roles. So I wanted to do both because often you see linear regression with W and B, and these are weights and biases. There's whole websites called Weights and Bias named after these parameters. But because it's a line, it's sometimes described as a slope W or an intercept B, like where the line intercepts the x equals 0 axis. But more generally, because we're eventually going to have many, many weights potentially, and we might run out of letters of the alphabet, we'll just use W for weight and have weight sub 1, weight sub 0, and so on, as we've had here. Right, so weight sub 0 is multiplied by x to the power of 0, which you can't see, it's just 1. W sub 1 is multiplied by x to the power of 1, which is just x, and so on. But all of this is the same thing. So we have a example, x, the ith value of x and the ith value of t. So our prediction will be to try to predict, in this case I'm also fiddling with things a little bit. So here yi is the prediction, before I was using hats, and f sub theta of x of the ith element is our prediction, and our residual, the actual error, let's see, the actual error is the prediction, which is y, the ith y, minus ti, right? We've been using these differences before between actual and predicted a lot. Technically, we'd call this the residual or the actual error. And again, we want these residuals to be small in magnitude as much as possible, right? So sometimes you don't care if it's a positive or negative difference. We want these to just be as close to 0 from either side as possible. So again, we have the squared loss. We compare y and t. We subtract them, we square them, and divided by 2 on a single data point gives us the squared loss. On a whole data set, the empirical risk will look like this. So here we still have the target t, which we're subtracting. Over here on the left, which I can't really highlight, so I'm highlighting it with these little ripples. We have our function. So w sub 1 of x plus w sub 0 is our function, our model. W sub 1 and w sub 0 are our parameters. So together, this gives us our prediction. So these two terms come together to form one prediction, minus the actual label, that's the residual. We square it. We sum up over all of the examples we have, and then we normalize by 2n. So training in one-dimensional linear regression basically means finding the best parameters that minimize this function. I should have gone back a second. So often, like I mentioned before, that the empirical loss can sometimes be referred to as the objective function. The objective function often is just, for the sake of tradition, is usually represented by j. So j represents like our empirical risk, right? So just like we wanted to minimize empirical risk, which we previously said was like capital L hat, same idea. I'm just giving you different representations of the same idea, just so you don't get confused when you see the same idea represented in different ways in practice, which you almost certainly will. So now we have in data space lines through points, which we get from our model over here. And in weight space, we have a cost function, we have a surface as a function of W1 and W0. I'll make this a bit clearer here. So here we have just x and y. Okay, so here is our x, which is the only number we can pass into our regression. And we have y, which we're trying to predict. And all of these blue points are data that we've generated. You can check this yourself. Here's code for you to run on your own. Okay, so we have these blue dots. We have 3 possible regression lines. I mean, well, we have many more than that. We have infinitely many, but I'm showing you 3 of them here for different weights. So in green here, we have a W sub 0, that's a bias of 0.5. Like this is going to intersect at 0.5, and the slope is 1.5. The yellow line has a steeper slope of 2, and it has a somewhat higher intercept of 0.7. Okay, so you can see how changing these parameters will give you different lines in data space. This is data space because, as you can see, all of these dots represent data points. But W sub 0 and W sub 1 together are kind of, they're dimensional, right? You can represent them in different dimensions. And I can move W sub 0 and W sub 1 up and down in their respective dimensions. That is what is shown here on the right. So if I move w sub 0 towards the right, that means the intercept of these lines go up. If I move w sub 1 upwards on this right graph, in this white space, that means the slope is getting more and more steep. And you can kind of see that here. So this yellow dot over here represents this yellow line. So I have the intercept of 0.7 down here. I have the slope of 2. You can see how steep this is. And I plot this weight over here at 0.72, representing that dot represents this entire line. Hope that's clear. So lines in data space here are translated to points in weight space. You may want to pause here and make sure you get this, right? So this is really, really simple, but it's also really fundamental. Here's a little interactivity you can do to maybe help hammer this idea home. So here we only have 3 data points, I believe. Yeah, we have 3 data points here we're looking at. This curve represents our surface space, and as you can see from the bottom here, the floor of this graph is our weights. W sub 0 is our intercept, W sub 1 is our slope. And I mean, in this visualization now it looks like X and Y, but this is W sub 0, W sub 1. And I can move this along the lost surface. So when I'm moving my cursor here, I'm kind of moving a point along this surface. What this means is, like, maybe I can see here, this is the loss, or this is the rather the empirical risk. This is the mean squared error empirical risk. So you can see you can imagine any model here. So down here, these reddish dots or these orangish dots, these represent data points in our model. Let's see what this one is. These are different than the ones we saw a moment ago. But what this dot over here basically means is that we have a slope of 1 and an intercept of 0.5. Actually, I think this is the same. Yeah, so that's a bit different. So here we have a slope of sorry, let's see this one. Yeah, they're a bit different. So here the intercept is 0.8 and the slope is 2.5, so a little bit different. But each of these 3 dots represent models in terms of those 2 weights. But as you can see, I can move like anywhere along the surface. So any combination of intercept and slope of W sub 0 and W sub 1 gives me a different loss. Like I move up around this kind of like sheet of paper. This sheet of paper is my empirical loss on the data we saw previously. It's all computed in this code if you want to get into the nitty-gritty of it. But as you can see, none of these models are the minimum. So the minimum is kind of shown here in green. So the best possible model linearly is down here at intercept 0.59 and slope 1.32 approximately. Okay, so the idea here is maybe you start with a kind of a bad model, and then we're going to kind of slide down this surface until we get down to as low as possible. The lowest possible point represents the point in weight space in which the empirical risk is minimum. I think this is like a very nicely intuitive graph, so I want you to play around with this as much as you can. It's very simple, but this will hammer home the idea of what we're doing, right? We have a loss function that defines average loss over all of the data we have, and we have an infinite number of possible lines we can draw through the space, represented by the infinite possible points in W sub 0, W sub 1. Each of those map up to a particular like risk on this curve, and we can find on this curve like the lowest possible point, which is down there. Moving on. So we have a toy exam set here. Again, as always, click on the links to click on the code to get it, copy it, run it. We have some of the data shown here is hours studied, and then the exam score. So this particular person studied for 5.35 hours and got a score of 70.9% on their exam, and so on. Is there a relationship between the number of hours studied and the exam score? Well, it certainly seems to be. So you can walk through this in your own time. This is another linear regression. What we're doing with this fit function is basically moving down that surface we saw before until we get to that point which has the smallest empirical risk, the smallest loss on average. And then we have, from that point, we have a particular value of W sub 0 and W sub 1. In other words, the intercept and the slope of this line, which is shown here in red, which you can see here. And you can also see, sort of by looking at all of these data points, you can see, well, what it actually, like what the values actually were for these data points. And you can see what the model predicted at that value of x. Okay, so here for hours studied 6.66, the model predicts a score of 82.8, and the actual score is 78.8. So there's errors. So in data space, we have a scatter of data points, and we have a fitted line between them. In weight space, for 1D regression, the cost, in other words, the objective function, in other words, our empirical risk, or average loss, is a quadratic and convex function. It's convex in the sense of its like bowl-like shape, and it's a function over our weights w sub 1 and w sub 0. And you can visualize your loss function over your parameters using a grid, basically, of values of w sub 0 and w sub 1 here. So this is kind of a topology graph where you can see like the amount of error is represented by these curves. So every point on this purple curve that I'm showing over here has a empirical risk of 50. Everything on this purple curve has an empirical risk of 100. And just like a topology map of mountains and valleys in your city, you can see that when we can move down this curve, we can move down this curve through the heights. It's not 150 kilometers, 100 kilometers, 50 kilometers, or meters. This is empirical risk, but the idea is the same, and we want to get down to this minimum point down here. Okay, so again, the code is all here. Please run it and understand it. So why is this J function quadratic and convex? So why is it quadratic? So every term here, every loss function, is a difference between our prediction and the actual, and it's squared. So this is a square of a linear function in w sub 1, w sub 0. Right, so the square of a linear function in just these two variables. I mean, variables in weight space, w sub 1 and w sub 0. Again, we're dealing with moving around weight space now. So like x is somewhat immaterial at this point. So if we expand this square, if we kind of distribute the square and expand it, we get terms like w sub 1 squared, w sub 1 times w sub 0, w sub 0 squared, etc., and we get a constant. And when we average over I using factors of this form, this will give you a polynomial of degree at most 2, right? So when you distribute the 2, this will be a polynomial, and you'll have it at most, the square. You won't have to the power of 3 or 4 and so on. And because the function is at most of squared, this is what we call quadratic. This is a polynomial of degree 2, in other words. This won't matter so much, and in fact I should probably have the microscope here to mention that this is sort of like zooming in a little bit, but this can be important in real machine learning. Why is the objective function convex? So z onto 1/2 of z squared is convex on here's a link actually for you to follow up on. It's convex on the real values. Every term in our residual of our prediction, which is these two terms, and our prediction here. This is an affine, in other words, linear and constant function of w sub 1, w sub 0. This convex function is composed with an affine map. This is going to be convex, and an average of convex function is also convex. Therefore, because an average of a convex function is convex, we're taking an average of a convex function. Therefore, J is convex. Therefore, it's convex in w sub 1, w sub 0. I made a slight error here. So on the right-hand side, I'm using w sub 1 and 0, and on the left, I'm using the other form, w and b. But by now, you know that w in that way of looking at things is equivalent to w sub 1, and b is equivalent to w sub 0. So this one bowl shape, this kind of bowl shape we saw in a previous graph, is why what we call gradient descent works so reliably for linear regression. We'll talk a lot about gradient descent later, but that's why we can quickly just go down the bowl and find our minimum point, as long as we have that gradient function. If we have a quadratic and convex function, any local minimum is also a global minimum, right? We're going down, is following the curve of the bowl downwards. We'll find the absolute minimum in this entire space of possible weights. So here's a little animation. You can run this yourself also. So we're going to start with an initial parameterization. It's down here at minus 0.50. And then gradually we'll take steps through this white space until we get towards the absolute minimum, which is this blue X over here. So let's see if this works. So very good. You can see that like these points over here, these orange points represent parameterizations during different steps of the algorithm. So we start with a pretty bad estimate, which has a pretty high loss way up here at the top of the bowl. But then because the change in the shape of the bowl, like it decreases fastest in this direction, down these curves, down the bowl, you can see I very quickly jump very far way down the bowl down to the second parameterization over here. The bowl gets less steep as we get down to the bottom, so the jump in the direction of the maximum change is going to be a bit smaller on the second iteration and even smaller on the third iteration. Now when I get to this point, I kind of hit kind of a curve in my path, and now the direction of maximum change will be directly towards the X, sort of like in that upper left-hand corner direction. And now like the changes are getting very, very small, like the curve of the bowl is becoming very, very shallow. So the changes from step to step are getting slower and slower, and I have to kind of inch my way towards the goal in the end. So this is what machine learning is doing. I start with one set of parameters, and I eventually try to find a set of parameters that minimizes my expected loss. So here's a bit of mathematics for this. Again, don't be scared if any of this is challenging. It really shouldn't be. This is pretty straightforward, and I don't mind spending as much time as needed with you working through these examples. So here's our standard form. We're still dealing with this linear function. So here's our linear function. We take the residuals, the differences for each of our data points as predictions and labels. For all of our data points. Here, when I take the residual, or so the differential of our objective function with respect to W sub 1, this is going to be a bit different. So I might have to go back a few steps. So before, you see over here, this is my actual objective function. Okay, and I'm taking squares of these differences like I've been doing throughout many examples, right? If I'm going to take the differential of this, I have to, like the differential of some function of x, some function of something I care about. In this case, I care about, say, W sub 1, is that function itself times, it's going to be 2. I bring down the exponent times the function times the differential of that function with regards to that weight, that variable I care about. So the differential of this entire component over here is going to be, 1/2 times 2, because I bring this down, times everything that's in these brackets, times the differential of what's in these brackets, so the partial derivative, with respect to W sub 1. So there's no W sub 1 in this term or this term, so these just go to 0. So I had nothing. W sub 1 is the variable I care about. X can be treated like a constant here, kind of. So when I take the derivative of like a constant times the variable I care about, the variable goes away. Again, I take the 1 off, the invisible 1 that's sitting up here above W sub 1, bring it down. All I'm left with at this point is going to be the constant, which in this case is x, somewhat confusingly. So that's what's happening here. So the derivative of my loss function with regards to W sub 1 is like my overall loss function, but I've taken down the 2, and that's why I had the 1/2 before, because I needed to get rid of it through my differential. This makes the math a little bit easier. So I don't have to keep on dividing my things. And then I keep everything that's inside of that, the parentheses. So that's pretty much unchanged. And then I multiply that by what's in the parentheses, the change in what's between the parentheses according to one of the variables, W sub 1. And as I mentioned before, this term over here goes to X sub I. This term goes to 0. This term goes to 0 because W sub I is not in those latter two terms. Hope this is ringing some bells. I think you've all seen calculus. So you remember how to take differentials for polynomials. and how to do that when we have polynomials of functions. But or you could, at the time being, you could let's take it as read that this is correct. If you want to prove me wrong, I would love you to try to do that. Similarly, we want to take the derivative of j with regards to w sub 0, and following the same kind of logic as before, we bring down the 2, that should be over here to the front. There was a 1 over 2 before, if you remember. There it is, so that cancels out. The 2 over 2 is just 1. We still have our parenthetical. That parenthetical with respect to w sub 0 is only in this term in the middle, has w sub 0. All others, this one and this one, go to 0. The w sub 0 kind of disappears, and I'm left with 1, which is invisible, and it's kind of sitting over here outside of the parenthesis. So why do I need to do that? Why did I have to suddenly do differentials? Well, we're doing differentials here, right? So we're caring about the direction of maximum change in this weight space as I'm moving from one parameterization or one model to the next. And I care about, the direction of maximum change in both of these directions. So that's why I'm taking the differential of this shape of the overall curve here, the bowl, with regards to w sub 0 and of w sub 1, which I have here. And now I can do my updates, finally. So I have my initial parameterization for w sub 1, and I can subtract from it the change necessary, which I get from the gradient, times some amount eta. So this n-looking thing is actually the Greek letter eta. This is a number I'll tweak myself behind the scenes in order to change how quickly or how slowly I'm changing my weights. But this update function of my earlier weight minus a little bit of a change defined by the direction of maximum change gives me a new w sub 1. So that gives me the change from this w sub 1 at 0 to this w sub 1 at approximately 0.7. And it also changed w sub 0 at the same time. So we can take a few steps. So go ahead and run this. Everything should be already, I think actually this code depends, does it? This might work fine for you, actually. So try writing this code in isolation. I don't think you need anything else beforehand. So here, in this code, what I have is a function of cost and gradients. So I have my weights, my slope, my intercept, my x, my given x, and my target t. So I have a linear function which makes predictions y based on the product of w and x and b. So this is my good old line with my parameters w and b. I'm given x as input. I have a prediction y. That prediction y is compared against my true target t, which I'm given. That's my residual r. So now I have the objective function j, which is defined previously. You can go back and check this, but that's basically just 1/2 times the average of the squared loss. So the residual squared. These 2 stars mean squared to the power of. Sorry, these 2 dots mean to the power of, and this 2 after these 2 stars mean to the power of 2. Now I have my functions here. You can go back and check it. I have the average. So the difference in j with respect to my slope is the average of my residual, which is everything in here, right? The difference between my prediction and my target, times x. You can see that down here. And it's the average, so I sum up over all of them and then divide by the total number of them. That's what the mean is, and I store that in my d of j given d of, or my differential of j with regards to my weight. And I do the same thing over here. My d of j with regards to the bias, or the intercept, is just the average of the residual, which I have down here. And now I have my overall empirical risk j. I have my changes in j with regards to my slope and my intercept, and I return all of that from this function. Okay. I'm going to start with an initially bad guess of -2 and 20. And then I'm going to have eta of 1 to the power of -3. So eta is this n-shaped thing over here. This is essentially my learning rate. How fast do I want to learn? And I or you apply this ourselves. We're going to have a little history, which is going to save our progress. And now we can just step through a range. So we have our weights bias. So for every step of the process, we have our weights and our bias, or like our parameters, which we have previously defined badly. We have hours and score. Actually, yeah, so going back a sec, if you were to run this code in isolation, it wouldn't work. You have to first run the code that generated the data from a few slides ago. So a few slides ago, I generated a data frame or a data set with hours and scores. You have to go back and run that first, in a cell in your Jupyter notebook or whatever. So we actually have data here, so we can compute these losses and these risks and so on. Anyway, we have our data, we have our inputs, we have our targets, we can make predictions given our parameters. This gives us, our empirical risk and our the directions of maximum change. We can just keep on adding these. This is how we're going to store our models for the time being. And then we can do our update. So just like before, where the slope is the previous slope minus eta, our learning rate, times the differential of our objective function, the big bowl, with respect to weight. That's this line down here. And this math over here is converted to this line over here. Again, I'm going to mention this several times, but the pure math, which is what we see in research papers, how we'd actually communicate to each other on a whiteboard, very precisely. This is all written down here, but it converts directly to math, to code rather. So Python and math are basically two views to the same phenomenon, which I find really great. Anyway, so I'm going to run through this sequence for the first 120 steps. I'm going to try to run this 120 times and get 120 better and better estimates for my model. And then I'm just going to print like the last 5 of them. So I'm storing everything in my history. -5 is just go back and take the last 5 that were appended, and I see them down here. So here I have my final loss here. So my final empirical risk is 123.42, which you can see is less than it was previously, which was less than it was before that. So you can see the empirical risk keeps going down and down and down as we keep moving. These first 2 numbers here are parameters, like I'm printing W sub 1, W sub 0, and that's our slope and our intercept respectively. Or weight or a bias if you care for that. So let x be a real valued vector. So d is more than one input variable. So before x was just one number, now we're going to have x input being represented by several numbers. It's a multi-dimensional vector. Okay, it's not just a single value of x. There's many values. We can still stack the data into this matrix. We talked about this earlier. So our big input data, big X, will be some type of real valued matrix with n rows and d dimensions, because we have d, like every data point is represented by d numbers. We'll still have parameters. Our weights now will not be just a single number, but because we have a multidimensional space, our weights, or our slope, will be still called W sub 1, but now instead of being a single line, it's going to be like a plane or a hyperplane in d dimensions. And our bias, because our plane in 2 dimensions is still going to intercept our prediction axis at a particular point, that point is still a real valued number. Okay, so our predictions now are going to look like this. It's still linear. Now we have like a big X, which is a matrix multiplied by our weights plus 0. This is going to be our prediction. We have this bias trick where we can add a little bit of extra information here. X tilde often is what we call like X, or variable X, and a special 1 at the bottom of it. And we'll see why this is useful a bit later. Our weight matrix is still our weight matrix is going to be the combination of our slopes and our intercept. So our empirical risk will take a very similar form as before. It's still 1 divided by 2n. And now we have this double bar equation. So this is going to maybe be a little bit atypical for you. Maybe you haven't seen this, but what this means is like the 2 norm. And we still have our residuals, so we're still taking our weights multiplied by our inputs, or our slopes by our inputs, and our intercepts multiplied by just 1, or like the identity matrix. We'll subtract t from that prediction, and essentially we'll be squaring these d-dimensional shapes. So it's basically the same thing as before. The only kind of real difference at a high level is that we are dealing with multi-dimensional inputs instead of a single x as an input. Luckily, this is still going to give us a convex quadratic equation, or like J is still a bowl shape in W sub 1, W sub 0. It's just going to be a bit harder to visualize because now we have more than just 2 numbers that describe our weights, because W sub 1 has multiple components to it. So real relationships are not going to be linear necessarily in X. What we would like to have is some kind of feature map, phi of X, to build nonlinear models while keeping linear parameters. So an example of this is to multiply our parameters by itself a certain number of times. So we have x squared, x cubed. This is a degree 3 kind of representation of the polynomial of x. And we can transform what was previously just a linear function of weight sub 1 times x plus w sub 0. Now we have squares and cubes of x. So we're still just given x, but now we're taking squares of it and cubes of it in order to get a more complicated function that isn't just a straight line through the space, but can be more wobbly. Okay, we'll see examples of this soon. So first we choose phi. Choose phi will convert a d-dimensional space into a k-dimensional space. We'll have an original model, f of a parameterization theta of x now is sort of a weight matrix multiplied by phi, which is our x squared, x cubed. I mean, this is a fancy way of basically just saying what we have over here. So as you can see, f sub theta x, this is the same thing. This means the exact same thing. It's just that here we're writing it out in full, like we normally might see it. And here we're writing things out as if it's a vector, right? So we have a vector of x's, we have a matrix of weights, and we just want to multiply those things together. So this is easy for us to visualize because we're used to seeing this as humans. This down here is how a computer prefers to see it, as like matrix multiplication. All of our earlier linear regression math will still work, but the function of x will be a nonlinear function. It won't be a straight line. So again, here's a tiny little data set, a smooth function. You can see how I constructed it here as a sine wave, consisting of, there's a pi component, there's x train. Anyway, so the true function that's generating my data is this dashed orange line down here. Okay, these dots are what I've sampled. This is my training data. So that's like noisy samples. Like I tried to estimate it, but maybe the sensor was a little bit off, in some sense. There's some noise in the channel. So the measurements I'm obtaining in X are not exactly, exactly what the data generating process generated. And these colored lines we're going to see are going to be fits to it. So right now we have a degree 0. The degree 0 doesn't even care about x at all. It's always going to predict the same value of y, which we can see this line over here, which doesn't seem to be a very good prediction of these points. You can go ahead and click that off, and I'll click the linear one. So this is what we've been dealing with this whole time. This fits a single line through these points. So now we're not dealing with multidimensional data. Again, x is just a single number, okay, just to make that clear. X is, the sine wave is generating data points. All I have access to is the data points. I don't actually know that it's a sine wave, so I decide I'm going to fit a line through it. And this is the best possible line that minimizes the loss on average of all of these data points. Okay, better than degree 0, but not great. I can go to degree 3, right? So degree 3 means I have x cubed times something plus x squared times something plus x times something plus something. And that gives me this orange curve over here. This orange curve seems to be much closer to the truth than either degree 0 or degree 1, right? So I seem to prefer degree 3 I seem to prefer the function where x is cubed to the one where it's just a straight line. So things seem to be getting better. When I add, higher degree, so maybe it's even better when I take x to the 9 plus x to the 8 plus x to the 7 plus x to the 6 and so on. Maybe I just make my function as complicated as possible, and that's going to give me a really good fit over here. Okay. Now suddenly things seem to be getting a little bit weird, right? They're not drastically weird, so generally the overall shape still follows a sine wave. But there's this weird kind of bump over here, this kind of a weird bump over there. And what's going to slowly start happening is that as I'm increasing n, as I'm increasing the degree of these curves, the curve will sort of shift away from the truth. So as you can see, this blue curve, this higher degree, more complicated, more wiggly curve, is further away from the truth than my orange approximation is, right? Sometimes it's closer, like down here, but often it's worse, It's worse everywhere from here. It's exactly the same over there. It's worse. It's there it's a bit better. There it's worse again. So it's not universally the case that making models more and more complicated will make the estimation better. Will make the empirical loss smallest. So this is true. This is truly what these curves actually look like. This is if you can generate it yourself and play around with it. In fact, as always, please play around with it as much as possible. This is based on this book here. So this book from Bishop has these images in it, which tell the same story, but in a somewhat exaggerated way. So here's our zero order curve, which doesn't care about x at all. It always predicts the same target. Here's our first order line through our data. So again, all the data is these blue circles. Green is now the truth. Red is our model. We get better with m is 3, so we have a third order polynomial, and now this is fitting fairly well, certainly better than 1. This is where things get kind of crazy. So now we have a ninth order polynomial, so x to the 9 plus x to the 8th, and so on, all multiplied by coefficients. And in the book, this shows wildly fluctuating a curve here in red. So this curve has actually minimized the risk on data. So we seem to be doing better on training data because unlike any other example here, my red curve passes exactly through each of my data points, meaning that my loss or my residual on each of these data points will be 0. So the average will be 0. So on training data anyways, this curve looks to be the best. But if suddenly I got new data, I got new samples from this data generating process, P in the world, I sampled something here, somewhere between these first two dots, the model would predict something way off the chart, which is obviously very, very wrong. And suddenly the model, which seemed so good in the training environment, will look like rubbish when you deploy it. And then you're going to get very embarrassed, and then you'll wish you paid attention in 3151. So let's solve this with sklearn. So we can actually go ahead and do this. I'll leave this as an exercise for you. So again, the code is on the website. We have the degrees of 1, 3, and 9. Instead of actually coding everything up ourselves, we'll just let sklearn do it for us. So sklearn has polynomial. It has mean squared error, which is all we really need. And then down here we fit the polynomial to our data. We provide the transformation. We do the linear regression. Everything we're doing so far is some modification of linear regression. Anyways, and then you're going to get your results, and you can look at your results down here. You'll have a training MSE. So this is how well you do in your in your lab, right? In your training data. So the mean squared error on your training data, when you're dealing with a single straight line, it's 25.9, and your validation mean squared error, like your validation on some held out kind of pseudo test data, is still pretty high. It's 27.2. As you generate more complicated models, the training MSE goes down, so we're getting better and better, closer and closer to the truth. Our validation MSE also goes down, so training empirical loss of 4 is way better than 26. Validation MSE of 4 is way better than 27, so it's a very small loss on average. But now we go to degree 9. We do our approach, our linear regression approach. And we have a training MSE, which is smaller than ever, barely. So 3.7 is not too different than 3.9. We're still doing better on training data, but then if you look at the validation data, the data that was held out and not used in training, suddenly we're starting to get a bit worse again. So more complexity here is translating into worse performance. Here's how we can visualize all of this. So just go ahead and look at this code if you want to. This is the value of x. All of these blue dots are data. This black dashed curve is the true function, which is generating all of these blue dots. The blue line over here is a degree 1 regression. The orange is degree 3. The green is degree 9. Generally, it doesn't buy you that much by going from degree 3 to degree 9. You might actually get worse error in validation and testing, like we saw a moment ago. But even if you don't, you're still expending an awful lot of cost learning all of these extra parameters, all these extra weights, which you'll never actually need. So, degree 1 underfits, it doesn't fit to the data very well at all. Degree 3 is pretty good, but degree 9 might be actually learning some noise now, and not just the true function itself. So let's switch to classification. So we have a binary label, which can be 0 or 1. We have a predicted probability, which is either somewhere between 0 and 1. We're not exactly sure it's 100% true or 1, but we're going to estimate a probability of 0.9 for this class. In classification, our loss, the thing we want to avoid is, if the prediction y hat and y are different. So if they are different, we have a cost of 1, or the residual is 1. We've seen this example before. This is very intuitive. So differences are bad and exact predictions are good. No loss at all. But there's no differentiable here. There's no differentiable component to this. Our empirical risk convex quadratic function we saw earlier, which we can kind of just slide down the bowl into the actual minimum, allowed us to find the parameters of the model that gave us that minimum. But we needed our differentials in order to find the direction in which things were changing in order to find that direction. All right? This function, this mere inequality, is not a differentiable function. We can't take the differential of an inequality function. So what do we do? Well, we can convert this idea into something called a logistic or cross-entropy loss. So we have the true output, y. This could be 1, for example. And then we multiply that by the log of p, which is the probability of our output on a scale of 0 to 1. So we want these values to be similar to each other. The log of 1 will be 0. The log of 0 will be negative infinity. And then we take the opposite case, so 1 minus y. So 1 minus y is sort of the opposite of the true class. It's the thing we're trying to not classify, times log times 1 minus p hat. So if p hat is the probability of true output, 1 minus p is the probability of 0 or false output. So combining these two terms together basically gives us a function of the probability and the true output, and the probability of the inverse of the true input. This is going to be smooth and convex, which is good for gradient-based optimization. So we can actually take differentials of this function, and it also punishes overconfident predictions very strongly. Just here's some examples to maybe make this a bit clearer. We have a true label 1, so this is a positive case, like the person has the disease, for example. Model A makes a prediction. Its prediction is not exactly 1 or 0. It's going to give you a probability. So its prediction is something like, I'm 0.9% sure that the label should be positive. So this loss is approximately minus log 0.9. Okay, so the true value is 1. The estimate is 0.9. 1 times log of 0.9, all minus. This minus will come into the parenthesis, is approximately 0.105. Model B is further from the truth. So the truth is 1, the model B estimates 0.6. Plug 0.6 into this term. This gives you 0.511. So you get more of a loss if you're further away from the truth. 0.1 is super far away from the truth. So this gives you minus 1 log 0.1, which is like 2.302, which is the highest loss we have. And that makes sense because 0.1 is the furthest from the truth among these three models. I should have mentioned one of the reasons why we have this these two terms, this term of y and this term of 1 minus y, is that predictions will either be 0 or 1, and we don't necessarily know beforehand which these are going to be. So we have to have a function that can accommodate both of those possible outcomes. So in this case, the true label is y. So we have y here as 1, and then we're dealing with minus log of whatever the prediction is. Okay, but because of that, because y is 1, then 1 minus 1 goes to 0, and then therefore this entire term over here goes to 0 also. So I'm only really comparing a prediction against how close it is to y, to 1 rather. If my prediction was 0, right, if the true label was 0 or negative, sorry, here we go again. I'm going to zoom out for your own benefit. So if the truth is 0, then y would be 0, and then high predictions of 0.9, 0.8 would be bad, right? And I want to see how close is my prediction to the truth, which is 0. So y, the truth being 0, zeroes out this entire term. But because now y is 0, 1 minus 0 is just 1. So now I'm really only like comparing my prediction of p against, I want to see how small it is. So 1 minus p would give me big values if I have very small predictions, which is good in this case because I'm going to take another negative. If p is very big, then 1 minus a very big prediction, like a 0.9, would give me a very small number. A log of a very small number is going to go down that log hole down to like closer and closer to infinity. And when I minus it, it's going to be a very big number. So, the point of this is it's kind of like a switch. So you can think of this these two terms as a switch. If y is a positive case, use this term. If y is a negative case, use that term. And then just basically these logs calculate how far away I am from the truth in either case. Hope that makes sense. I think that's a kind of a beautiful, beautiful, simple way to think of it. Anyway, this is kind of like an approximation of confidence. So like you can use these numbers not just as like errors, but in terms of confidence. So naive regression is a bad classifier. This is, I think, the last thing we're going to really talk about. Our scenario is this. We have features. Back to our earliest example, we have videos watched in the first few days, and we have the average quiz score and percentage. These are our inputs, and we want to estimate, our y's are 0 or 1. 1 is the person gets an A+, which I hope you all get, and 0 is they did not get an A+. So it's a positive case and a negative case. So the naive idea is to treat y as like a real valued target. I'm going to do good old-fashioned regression. I'm going to fit a line or a curve to these data, and I'll fit that with a squared loss like we saw before, and I'll just have a threshold. Like if the prediction is above 0.5, I'll predict that they're going to get an A+. If it's below 0.5, I'll predict that they don't get an A+. So this technically gives us a classifier. So I will be able to learn a line given all the dots I have, all the data points. I'll have a threshold, which I supply myself, and then I can just compare predictions to that threshold, and then that's a classifier. But unfortunately, a line through the space can go to less than 0, which doesn't really make sense. Like my predictions are either 0 or 1, not less than 0 or greater than 1. So how do I deal with those situations? A squared loss really is misaligned with the Bernoulli structure. I may come back to Bernoulli later when we talk more about math, but this is basically like a a sampling of binary outcomes. And also, like, overconfident wrong predictions aren't really punished enough. And I see this in this example here. So we have ground truth function. We have randomly generated data. We have 400 data points. We have a number of videos watched. We have a number of quizzes and like the scores on those quizzes. The average score on these quizzes is 70. These are normally distributed variables. We have a ground truth logistic model for activity. So we have like the true values of our weights and biases. And then we just produce our logits and our probabilities, which I think we can skip over for now. And then we have like our outcome. Active is whether they get an A+ or not. We put our data into a pandas data frame. We do some clipping. We pull out our values. We do the train test split. We learn a linear regression on our training data. We then use our linear regression classifier to predict on our test data if it's if our predictions are above or equal to 0.5, we get a true. We send this as an integer 1. That's our test outcome. Otherwise, this is false. We convert this to a 0. That's our outcome for that prediction. And then we can do an accuracy score, which is like a simple measure we get from sklearn. Play around with this as much as you can to be as familiar as you can with what I just did. But what we have at the end is we have our predictions for our test. Here's our 5 predictions. So, I mean, the numbers might not mean anything to you right now, but we predict 0.51, 0.66, 0.25, etc. So these are all predictions of our linear model. And then we have our accuracy. Our accuracy is 82.5%. The naive predictions are going to follow this kind of curve. So I haven't included the code here, but I've kind of graphed the predictions made by this linear regression model on our data, and 12 times, or approximately 12 times, the predictions were somewhere between 0.3 and 0.4, which is this histogram here. It more or less follows a linear model, actually, in terms of our predictions. Sorry, a Gaussian. Sometimes I make predictions less than 0. Sometimes I make predictions greater than 1. So that's not great, but this sort of just confirms what I mentioned earlier. This threshold of 0.5 is right down here in the middle, and this is arbitrary. There's so many data points that predictions are between 0.2 and 0.8. It's not clear that there should really be a separation here. There's no separation at all, actually, in this image. This is what it looks like in the data space. So again, look at the code if you want, but this kind of demonstrates why linear regression is going to be a bad outcome for this kind of prediction task. Here's all my negative cases. Here's my predictor X, and here's my Y outcome values. I've added some noise, so as always we add some noise. Actually, that's not true. Sorry. All these data points, they're all Y equals 1, but the noise is kind of added just for visualization. These are all zeros. These are all ones. I fit a straight line through all these zeros and ones. I get something like this, which doesn't really follow the shape of these dots. So the ideas in this module will scale up. Large language models are trained with token level cross entropy loss. So the cross entropy we kind of introduced very briefly earlier. This scales up, and this is what's used in large language modeling. Image classifiers also optimize cross entropy over maybe thousands of classes. So instead of just having a positive and negative case, we're predicting one of potentially thousands or tens of thousands of classes. Deep neural networks are also compositions of linear maps. So we often have linear functions and nonlinear functions within very deep neural networks. These are trained also by gradient-based optimization. So if you don't understand what we did before with taking gradients to kind of move down that empirical risk bowl to try to find the minimum, go back, ask me questions, because gradient-based optimization is really like how we do machine learning almost all of the time. And it's still computed over a data set. So the fundamentals of what we did scale everywhere else. If you understand how we've gone from taking data to getting a model, like a family of models or a function, getting a loss function and transforming that into like average loss or empirical risk, that's going to be good. If you understood the basics of linear regression, that's good. Let's see 1 second here. We haven't actually talked about logistic regression at all. That's going to be in a future module. So if you understand linear regression only, that's a good thing. And if you understand what gradient descent is kind of doing, so a gradient basically just defines those partial derivatives. We want to descend down the space towards a minimum loss on average. So following this negative gradient in weight space, remember, because the space of that loss is in terms of W sub 0 and W sub 1. If you understand the basics of that, that's fantastic, because you are now up to date with the core template behind much of modern machine learning. So we're doing really well. Congratulations. So in future modules, we'll actually explain how we can go from this form of regression to a much more well-fit model of regression. Looking forward to that. See you next time.